All right, so we're gonna quickly discuss question 4, which actually covers which is focused on topic 4, and we're gonna quickly discuss that and solve again the question paper. So topic 4 is about binary decoding and loading software onto a computer. So okay, so on the first model, or the first point, it's all about Boolean algebra. So in Boolean algebra, you guys should study the logic gate and the Boolean expression. I don't think we have to come back on the logic gate. We have done enough of logic gates. So if some of you are struggling with the logic gate, you can check level 2 videos, which we have covered logic gates and Boolean expressions. I think that would be enough. So if you're struggling, check level 2. We are discussing question 2 for level 2, where we touch deeply into logic gate and the Boolean expressions. Okay, so you're gonna have to study the rules of Boolean algebra. So first of all, you should be able to define the different laws in Boolean algebra. So you should be able to define commutative law. So you should be able to define them, and then associative laws. So you should be able to define associative laws, and then distributive laws. So you should be able to define these laws. So after defining these laws, then you should be able to read all the, I think it's about 12 rules, if I'm not mistaken, of a Boolean algebra. So usually they will ask you questions on the rules, or they will give you small problems where you have to apply those rules. All right, so you go through the De Morgan's theorems. So yeah, you go through the De Morgan's theorems. So that will be all. Maybe we're gonna bump into some questions in the question paper where we're gonna have to solve some of these rules or theorems. Okay, point 2, which is talking about binary code. So point 2 is about binary code. So where we learn to convert decimal to BCD. So we have two types of BCD code. There is a video in our past tutorials where we've done this, so we just gonna see. Probably there is always a question about converting to BCD code, so we're gonna have to solve that question directly. But if you want to learn deeply in the BCD code, so you're gonna have to watch our previous videos on the BCD code, how to convert from decimal to BCD code, or from BCD code to decimal, because you have both of them here. So there are two types of BCD code. There is 8421 code, and there is 2421 code. 2421. So actually this is some combination that helps you write a binary equivalent, because this is the BCD code actually. So it helps you write the binary equivalent. So for example, if they give you a number like, let's say they give you a number like 9. So if you have a number like 9, so in this code 8421, which numbers, if you put together, will give you exactly 9? It's gonna be 8. So on 8 you're gonna put a 1. It's gonna be 1. So 8 and 1 will give you 9. So the rest is gonna be 0. So that's how it works. So if you watch that video, you're gonna see how easy it is. So the 8421 code, that's how it operates. If they ask you to convert a 9 into a 8421 BCD code, so that's how you do it. So 9 is going to be the combination of 8, you write a 1 under 8, and 1. So 8 plus 1 gives you 9. So you're going to write a 1 here and a 1 there, and the rest of the digits would take a 0. If they ask you to write let's say if they ask you to write 7, let's say 7, a 7. So a 7 in BCD 8421 code is going to be, which combination will give you a 7? That's going to be 4 plus 2, that's 6 plus 1. So you're going to have a 1 here and a 1 there and a 1 there, and here it's going to be a 0. So that's how it works. And the same thing if they ask you to write, for example, let's say they ask you to write a 5 in a 421. Let me do this number first. Let me do it in 8421. If they ask you to write a 5 in 8421, this is how you write a 5 in 8421. So it's going to be a 4. So you're going to write a 1 on 4. That's how it's going to be. 1 on 4 plus 1. So that's going to be 0, 0, 1, 0, 1. So it's going to be 1 on 4 and 2. But if they ask you to write a 5 in 2421, you don't want to repeat the same thing, because look, if you repeat 1 and 1, 4 and 1 gives you 5. If you write a 0 here, it's going to be the same thing. So to avoid this, the 2421 code, if you want to write a 5 in a 2421 code, you're going to have to do 2 and 2 and 1. So there's a be a 0 there. So I believe, so we are avoiding to repeat the same thing. So we make a combination of 2 and 2 and 1. It gives us a 5. So you put a 1 under 2, you put another 1 under the other 2, and then a 1 there. So it's actually easy. If you check those videos, you're gonna be able to solve these ones. Very easy. So it goes the same if you have to convert a number from BCD to decimal. Same thing applies. Alright, so converting, the same thing. If you follow our video, exercise 3 also is explained deeply there. Please study this. There was usually 1 or 2 questions on alphanumeric codes. I'm not sure if in the past tutorials we have done it, but usually they will give you a number. Let's see if we're going to have an example. They will give you the code of each alphabet, and later, for example, they're going to have a different code. Now they might ask you, for example, to write the word, for example, big in a code. So you have, if the examiner asking you the question is going to give you exactly the code for B. Let's say, for example, it might be 0, 1. I don't know the code for B. I'm just assuming 1, 2, 3, 4, 5, 6. I'm just assuming. So, and then the code for I, maybe even 0, 1, 0, 0, 1, 1. I'm just assuming. So what you have to do is, if they ask you to write a B, the word big in alphanumeric code, all you have to do is just collect the code for each letter. For example, if B was 010101 and I is 010011 and G is, so you just write the code for each letter. So that's how you write a code for alphanumeric code. It's the easiest thing ever. Binaries for level 4 is the easiest thing ever. So, and then floating numbers. So let me remove this. Let's do floating numbers. Floating numbers. Converting decimal numbers to floating numbers. So how would this go? I need some space. Alright, floating numbers. That is point 6. Floating numbers. So when we are defining a floating numbers, we may be dealing with decimal number. We can do a floating number of a decimal number or a floating number of binary number, but the procedure or the steps are still the same. When you must first define a mantissa of that number, and then the exponent of the number, and then combine the two of them to get the floating point, the floating point of the number. That's it. So you write the same thing. The mantissa, we're gonna explain what they expect you to do when it comes to a mantissa number. So and then the exponent of the number, and then you combine the two, you get what they're expecting you to do. For example, if they give us a number like, let's start with the decimal number. So they give me a number like let me say they give me a number like 12,385. This is a decimal number. We know this is a decimal number. So that's a decimal number. And let's get a binary number. They give me a number like 10101. 101. I'm just going with numbers. That we know it's a binary number. So when they ask you to find the floating point of this number, decimal number or binary number, actually I was supposed to do the binary one here. So what do we do here? First we said we must find the mantissa of this number. So here a 0.7 is actually for binary. I was supposed to do this here. 0.7 is for binary. 0.6 is for, so 0.6 is for decimal, 0.7. So decimal number given to us is 12,385. To write the mantissa of this number, we just add a 0 before that number. So 0.12385. That's how we write it. And the exponent, how do we write the exponent? The exponent will be, you count from the comma, 1, after the comma, 2, 3, 4, 5. So actually you're going from here, 1, 2, 3, 4, 5. The exponent is 5. That's how it is. And then to write finally the final answer, you're going to come, so your floating point of the decimal here, the floating point of the decimal is 0.12385 times 10 to the power 5. That's what it is. That's how you write it. That's the floating point. So this is the final answer after you've determined the mantissa and the exponent. That's what you write. So let's go to binaries. For binary, it's a little bit tricky. When you're writing the mantissa of binary, you don't put 0 comma. What do you do here? You just take the number that was given it, you just split, you put a comma between the first two numbers. So the mantissa is going to be, so you're just going to have to put a comma here. That's what we do. So you bring that number here. It's 1. Let me rewrite the number 1, 1. Let me create some space there. So it's 1, 1, 0, 1. So it's a 1, 0, 1, 0, 1, 1, 0, 1. So the mantissa would just be to come here and put a comma here. That's it. And the exponents now we count from here. 1, 2, 3, 4, 5, 6, 7, 8. So that's it. 8. So our exponent is 8. But since we are writing the floating point for a binary number, our floating point is going to be 1.1010101 times 2. Why? Because we are in binary. Here we did times 10. Here we did times 10 because we were in decimal. Now we do times 2 because we are in binary to the power 8. And that is the floating point for the binary number. And that's it. So this floating point is the result of this here. This one we have termed here. That's it. Easy as that. Easiest thing ever. First we define what is an encoder. Then you're going to have to draw a circuit diagram. An encoder is a circuit, or it's a system An encoder is a circuit or it's a system that converts decimal inputs it converts decimal inputs into binary outputs. So that's actually would be the clear definition. So convert decimal inputs. And there was a question where they asked to draw the block diagram of a general encoder. So a block diagram of a general encoder should look like this, because sometimes they might ask you to describe or define or explain what you understand by an encoder. Sometimes they would just ask you to draw the block diagram that explains what is an encoder. So you have decimal inputs. So you have decimal inputs. The decimal numbers start from 0. So you have decimal input. You're supposed to have 10 inputs there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are the decimal input. So we take decimal inputs and we convert them. So in encoder, we take decimal inputs and convert them into binary outputs. So on the binary, we're gonna have, this is the BCD, is gonna have a 4 bits, so BCD outputs, binary coded decimal. So that's your outputs there. So that's it. That's an encoder. Inputs, it's decimal. So we put decimal input and we get binary output. So that's how you can describe an encoder. So with the same logic, if you are asked to draw 8421 BCD encoder. So remember, I'm not gonna have to draw the whole thing, but it's okay. So let me just draw the 8421, then you guys will have to figure out how to draw the other one. So this one is gonna look like this. So we're gonna have, so how many outputs do we have? According to our block diagram, we have 4 outputs, which means we should make provision for 4 logic gates there. Logic gate 1, logic gate 2, logic gate 3, and logic gate 5. So that's how it is. So this is where we get our outputs. So the logic gates that we're using are all logic gates, all gates. That's how they are, the all gates. So it means we're gonna have of 8421. So it's gonna be 8421. So and all combination here counts. So we're gonna have 10 input starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's what we're gonna have. This is a line for each input. So if you are asked in the exam to draw, this is an 8421 that I'm doing. You can see on the output. So if you compare here, you're gonna see here it says 8421 output. So you're gonna have to draw it like this. That's for the output, for input for 4, input for 5, input for 6 is there, input for 7, input for 8, and then input for 9. That's how it is. So for example, if I want to produce a 0 on the output, there is nothing here that corresponds to 0. So nothing is connected. If I want to produce a 1, So this is the gate. This one here is the gate that is in charge. So I'm gonna come here, put an input all the way to 1 there. This is my 1. I'm gonna connect that input there. If I want to write a 2, I'm just gonna take this output, this gate here that has a 2, and connect it all the way to 2. If I want to write 3, what do I do? For 3, this is the line for 3. This line here is the line for 3. If I want to connect 3, what do? I must connect a 2 on 3 and a 1. That's what happens. A 2 and a 1 will give me a 3. So on the line, you can see on my line of 3 there, I've connected this gates that gives me 2 here, and this gate that gives me 1. I've connected both of them to 3 so that I can obtain 3 on the outputs. Now if I want to write 4, I don't need many gates because I have a logic gates that can produce 4. So I'm just going to take that and connect it straight to 4. Now if I want to connect 5, what do I need? I need a 5 and a 1. 5 and 1 here. 5 and 1 will give me a 5. 4 and 1 will give me a 5. So what do? I take one input, connect it to 5, the 4, and go to 1, take another, connect it also to 5. There's my 5. That's how I get a 5. If I want to do a 6, so I need a 4 and a 2 for 6. So I come to 4, I'll touch 6 there, and I come to 2 also, attach with my 6 there. So now I'm on 6. If I want to write 7, I need all the 3 of them to write 7. So I'm here. I'm going to come to 7. There's my 7. And I'm going to come to 2. I can use this one. Connect to 7. There's my 7. And to 1 also. Connect to 7. So you understand the process. If I want to write a 9, if I want to produce a 9 on the output, so I need a 8 on 9 and the 1 on 9. That's how I obtain a 9 in the output. So that's how easy it is. So you can do the same with the 2421 encoder. And here there was another mistake. Define decoder. So if encoder is a device or a system that helps you convert a decimal into binary output, a decoder will do the opposite. A decoder, what will a decoder do? A decoder will convert binary input. So we take binary input to decimal output. So we take binary inputs and convert them into decimal output. So that's what happens. So the decoder is actually the opposite. So, and then they also can ask you to draw the diagram of a 8421 decoder and 2421 decoder. So you have to study the application of an encoder and a decoder. Define registers. So you have to study also define registers. So you have to be able to define register. What is a register? What is a register? Define register. And you should be able also to. So a register is actually a group of flip-flops which are capable of storing 1-bit information. A register is store 1-bit information. 1-bit information. So that's it. So and then name the 2 basic functions. So the 2 basic functions of a register is to store data storage, data storage, to store data, and data movement. So data storage and data movement. So those are the 2 functions of a register. So what is a shift register? So now you have to define also What is a shift register? It's a group of flip-flop arranged so that binary numbers stored in a flip-flop are shifted from one flip-flop to another. So that's mostly it's a system or a group of flip-flop that is arranged in a way that the binary numbers stored in it shift from one flip-flop to another. So there is a shift from one flip-flop to another. From one flip-flop shift, from one shift flip-flop to another. And then the types, so they will ask you to name the types of flip. They might ask you, because we don't know if they will ask. They might ask you to name the 4 types of flip-flop registers that we have. We have 4 types of flip-flop registers. So we have the serial in, serial out flip-flop. So we call them serial in and then serial out. So there are block diagram for each one of them. Then there are 4 types. So then we have serial in, serial out, parallel in, parallel out. Then you also have serial in, parallel out, and you also have the 4th one is parallel in, serial out. So that's it. It's a seesaw, it's a paper, it's a simple, and it's a peso. So that is serial in, serial out, seesaw. Parallel in, parallel out, paper. Serial in, parallel out, simple. Parallel in, serial out, peso. So you can just remember it as, that's the best way to remember it. Those are the types of shift registers. So they come also, they would ask you to draw the block diagram for each type of. So for example, I'm going to try to draw. So when you are dealing with serial in, serial out, that's what it. So for example, I have this type of flip-flops. So these are the block diagram. They ask us to draw the block diagram. So this is what happens with the block diagram. Serial in, serial out. It means the information comes in series, and they come out also in series. That's serial in, serial out. If they ask you to draw serial in, parallel out, so which means the information are coming in series, but they're leaving in parallel. So the input is series, serial in, and the output is parallel. So they're coming in serial in, parallel out. So like that. That's how they're coming out. Serial in, parallel out. So you also have the serial in. I did serial in, parallel out. So let me do parallel in, parallel out. Parallel in, parallel out. So the parallel in, parallel out is going to be like that. Parallel in, so you have information coming in parallel and coming out also in parallel. So it's something like that. And then the last one would be the parallel in, serial out. So let me rewrite it here. Parallel in, serial out. So they're coming in parallel like that, and they exit in series like that. So that's how it is. So you can go through them and in depth, and then so but that's mostly in general how it is. So point 1.113 application of shift registers. You can also study some application of shift registers. And the point 4, loading software onto a PC. Study some theories about loading software onto the PC, and that's it. So we're gonna go straight to the question paper. Okay, so we are back with 2023. So we're gonna solve question. We're starting with question 4. So we're going to solve question 4. We are back to 2023. So let's go straight to question 4. So question 4. Okay, define the following Boolean algebra laws. This should be easier. So when you read your notes, you can easily be able to define. So you can define them through with the formula. So you can just say, for example, with commutative law. So the order in which you OR. So to OR something is to use a plus. That's a OR. And to AND something is to use multiplication. So if you've done your logic gate, so you know that to OR something is to use a plus sign, and to AND something or to AND variable is to use a multiplication. So the order in which you OR variable like a plus b does not matter. A plus b is the same as b plus a. So a or b, that's how you read it. A or b is the same as b or a, or a and b, that's multiply, is equal to b and a. So they say the order in which you OR or AND variable does not matter, it will produce the same result. So that's it. And go and read about associative law, distributive law, and so on. So let's go to question 4.2. Question 4.2, they say convert the following decimal numbers to 2421. 2421. So the number is 6. We are going from decimal 6 to 2421. So 2421. So on this side I would do 8421 because the primitive, the original code is actually the 8421 code. So this is the code, 8421 code. So if you have to write 6 in 8421 code, so you understand that the only combination for you to obtain 6 is 4 and 2. So 4 gets a 1, 1 gets a, so 4, and that's 6, sorry, that's 6. So the possible combination for you to obtain 6 is 4 and 2. So 4 will get 1 and 2 will get 1. The rest will get a 0. This is the 8421 code. So that's how you obtain a 6. But they asked you to do a 2421 code. So you don't want to repeat the same. Look here. So if you follow 2, 4 and 2, you're probably gonna obtain the same result as the 8421. You can see it's the same because if you follow, so you don't need to follow that, because with the different codes 2421 you must obtain a different result. So if 42 gives you the same 0110, so you change the code, so 8421. So we are going to use 2 and 4 to obtain a 6, and the rest would take a 0. So 2 and 4 will give you a 6, so you write a 1 there, and the rest will give you a 0. That's how it is. So and then for 28, so if you want to do 28, this is what you do. For 28 you are doing a 2421. For 28, 2421. So here I'm gonna do the 2 for 2421, and then 2421. Here I'm going to do the 8. That's how you do this code. So each digit is going to be converted separately, then you put the number together. So for the first one we obtained, the answer was 1100. That's it. For the second one, 2. How do you write the 2? So the 2 is going to be the same as this one, so we're going to use this 2 here, this one here, not the first one, this one here. So if you watch our first tutorial, we explained why. So we use this one here. 1 is going to be on this 2. The rest will take a 0. So for 2, the code is 0010. For 8, we're going to use 2, 4, 2. So all the three of them. So because if you do 2 plus 4, that's 6 plus 2, that's 8, and then 0 there. So the collective answer now, 28, is going to give you 00101110. That's how you do it. Okay, explain the difference between an encoder and a decoder. That's the easiest one. We said an encoder will convert. An encoder is a device that will convert decimal to BCD, and then a decoder will take a BCD input, converts them into decimal output. So that's it. That's how it is. Explain 3 guidelines that has to be followed to prevent software problem before installation. So this is the computer part. We mentioned it earlier here. Go and study some theories on the computer. So that is loading software onto a computer. Read those theories on computer. So we should be able to answer this question. All right, that is for 2023 question 4. Let's go to 2022. So on the 2022 paper, remember we've also downloaded this paper still from NCV exam paper. So 2022 paper question 4 in 2022 paper question 4. So how was the question 4? Make a neat block diagram to illustrate an encoder. So we've done that. So we said an encoder is a circuit that will convert decimal input into binary BCD output. So on the output we have 1, 2, 3, 4. That's the 4 BCD output. So BCD output. In the inputs, we're gonna have 10 inputs starting from 0 all the way to 9. So we're gonna have different inputs there. These are the decimal inputs. So that's how you draw the block diagram for an encoder. So 4.2, draw a labeled 2-stage circuit diagram of a serial in parallel out shift register. So here we are not drawing. Remember, they didn't ask for a block diagram. They asked for a circuit diagram. There is a circuit diagram. Go read your notes. There is a circuit diagram. It's quite large. It's using a clocked D type flip-flop and some AND gates. So go read your notes, so you're gonna get the answer. On the textbook, it's a 4-stage. So you just have to remove 2 flip-flops and then you have 2 stages. So that's actually, it's 4 marks for that. And then they say convert 5 to, you see your BCD is always coming. Your BCD is always there. Convert 5 to 8421 BCD. Now they ask you to convert it to 8421 BCD. So what do we do there? 5 is easy, and 8421 is the easiest one. 8421 is the easiest. So all we have to do is 8421. So that's what we have there, and we are converting 5. So 5, 8421. Which combination do we make to obtain a 5? So to make a 5, the combination is 4 and 1. 4 and 1 will give you 5. So 4 is gonna take a 1, and then 1 also is gonna take a 1. The rest will take 0. So that's it. So your answer here is actually 5 base 10 in 8421 BCD code is 0101. That's it, BCD. So that's it, easiest thing ever. And then your floating point, the floating point is there also. So the floating point, we said to define the floating point, First of all, you must define the mantissa of the number. So mantissa of the number is actually, if it's a decimal number like given here, what you have to do is just put a 0 before the number that was given there. So the number that is given there is 1324042. So if I have to read it in full number, it's actually 123 there, and then 123. That's 1,324,042. So that's it. So, and then you just put 0 comma, that's the mantissa of this number. You just put 0 comma 1324042. That's how it. Then the exponent is going to be so the exponent, you just count from the comma here, 1 2, so you count 1 1 2 3 4 5 6 7, so that is 10 to the power 7. And then your floating point, your decimal floating point, is actually 0,1324042 times 10 to the power 7. That's it. That's how easy this is. So, and then do we have a 4.5? 4.5. So we have a 4.5. So 4.5, they give us a circuit with logic gate. So this is actually a NOR gate. So it's a greater or equal to 1 there, and there is an OR gate, so greater or equal to 1. So this is NOR. First of all, you must identify each gate. This is a AND, and then this is a OR gate. So now you have to know the Boolean expression, because they ask you for the Boolean expression for the whole circuit. So what is the X? What is the final expression for X? We know that OR is a plus, NOR also is a plus, but there is a bar, AND is a multiply. So that's what we do. So what are the inputs? For NOR, the input is A plus B bar. For AND, the inputs are A multiply, or A and B bar. And now all of them on an OR output. So you're gonna take this plus this. That's your X. X is equal to A plus B bar. So everything plus A. Oh, there was no bar here. This is an AND. It's not an AND. It's an AND. So this one here is just A times B. It's not a bar. If it was AND, then there was going to be a bar there. It's not a bar. It's just A times B. So A and B there. That's your final answer. That's your X actually. So that's it. And then 4.6, there's always a 2-mark question about computer. So give 2 problems that one might encounter when dealing with insufficient or outdated computer hardware. So give some solutions there. Read your notes on computer, then it's easy to answer this part. So we're done with question 4. We're gonna go straight to question 5. So we continue with question 2023 paper. So we're still with 2023 paper, 6 children 2023 paper, and we continue with question 5. So let's go straight to question 5. So what you understand. So question 5, actually this is topic 5. So the whole topic 5 is all about programming the PLC actually. So explain what you understand by the following terms and devices. So you're gonna have to explain what you understand by PLC. Latch. A latch is a retainer contact, a power retainer contact. So it retains power for an output contact. So it's a retainer contact. A rung is like a branch, but is like a branch, but in a PLC circuit. So a relay is a electrically powered switch and a CPU. So you're gonna have to explain all these terms in connection to either a PLC or any other automatic system. All right, so 5.2, we say the local can manufacturing company has requested you to write a program using a ladder diagram logic that will do the following task. Model A must start rotating immediately when you switch on the machine. So model A must start rotating immediately after you switch on the machine. So let me bring a new page. So model A, so that's my power line. So model A must start rotating immediately after you switch on the power. That's what it says there. So we're here. After 5 minutes, motor B must start rotating automatically while motor A is still running. So let's first do that one. So we do. So when you start the power, so that is how it starts. So we can call it x0. So that's the start button. So motor A start immediately. We're gonna add other stuff as we go. Motor A start running immediately. So let me call it MA. So MA start running immediately after. So we say after. So when you start, because it says after 5 minutes, then motor B start running. So what do? You create a contact that you are going to label motor A. So when motor A is running, I want this contact to turn on the on delay timer, because on delay timer T on 1, let's call it T on 1, which is the 5 minute. So T on 1 is on, so we label here MA. So motor A is on, and this contact is being controlled by the time on delay T on 1. So for us to control motor B, MB. So that's what's happening. So what's happening actually is when you press starts on XO here. So when you press start here, motor A start running, this contact close, the timer counts. When it reaches 5 minutes, it activates this, then the motor B starts counting. So that's exactly what's happening there. So let's read on. So it says this: motor B must start rotating automatically while motor A is, so that is after 5 minutes, is still running. Both motor must run together for 2 minutes, and then after 2 minutes, motor B must stop automatically. So something they did not mention is your latching contact. So first of all, okay, I was reading on to see that. So first of all, to keep the motor running, when you press start button, so when you press start, we need to create a retainer contact here, a latching contact here, that we also gonna label MA. So the use of this contact here is to hold power for the motor. So when you press start and motor A is running, when you release this contact here, the contact that we label MA is going to be holding power for the output, which is motor A. So that's actually why we put the retainer contact there. And what does it say? It says, so motor B is going to start running. So unfortunately here they are not telling us that we need to put an emergency stop button, but you can always make provision for an emergency stop button. But what's happening is motor B is gonna run for, so we want to also create another timer which which gonna be controlled by motor B. So the moment motor B is activated, we want this contact also to activate. So this contact is activated, and this contact is controlling the time on delay, on time delay, on delay timer 2, because that was on delay timer 1. This is on delay timer 2, which is 2 minutes. So the moment motor B is activated, this contact MB also activates, and the counter start counting. That's what's happening there. The counter start counting. They say when after 2 minutes, motor B is supposed to stop running. So what do? We come here also, we create another contact, but this is going to be now a normally closed contact that we are going to label MB. So what happens? So, well, no, we're going to label this contact, because this contact is only activate when the timer on delay timer 2 stops counting. So we label it on delay timer 2. So what happens here, when motor B is running, this contact closed, the timer starts counting, and when after 2 minutes, when the time is done counting, this contact here, T on 2, is going to open. When it opens, motor B is going to stop running. So that's how it's operating there. So there is need for an emergency stop. So there is always need for an emergency stop. We can always include an emergency stop that we can call. So this XO is going to be our start, and X1 is going to be our stop, emergency stop. So that's what's happening there. So we've actually, so you don't forget to always include your end, because there are marking guidelines that provide 1 mark for after you've ended your program. So you can just finish your programming like that, or you can just leave the spot like this, but include your end, and this is correct. So this is that. And let's go back to the question. Is there another question? 5 points. There is no other question, so that's everything. Let's go to 2022 paper. The 2022 paper, we still have the 2022 paper there. 7 November 2022. So what do we have there in question 5? Question 5, let's go down to question 5 somewhere here. Question 5, it starts immediately with they say explain the operation of this circuit here. So this is what we got. I'm going to create some space here so we can explain. So what happens here? The moment the circuit, when the system is powered, let's call it system. Let's call it the circuit. System, circuits, we're good. So when the circuit is powered means you just turn the power on. You did not start anything. You just turn the power on. So when the circuit is powered, it means when the power is supplied, what happens? CR2 is already running. CR2 is on. Why? Because we have a normally closed contact there. There is a because of the normally closed contact, CR1 is on, is active. So that contact here is active, so it allows, before even you press anything, CR2 is active. Now, when you press, when A or B, you can see this 2 here. This is an OR gate. So these two, this is not a latching contact because these are two separates. They have a different label, and you can see even the second one doesn't have the same label as CO1. So there's no latching. We explain this. Go check our tutorial. We're explaining when latching happens. So these two contacts A and B, they are in parallel. They are both controlling CR1. So if one of them is active, if A or B is active or turned on, activated, what happens? CR1 start running. CR1 is on, and check what happens when CR1 is on. Any contact that is labeled C1 also receive some action. In this case, the CR1, the normally closed contact CR1 turns off. And then when it's off, what happens? When it's off, CR2, then CR2 also turns off. That's what happens. So that's actually, in short, the explanation of this diagram. So they ask you to explain the diagram, how it operates, and that's how easy it is. Observe everything in the circuit, all elements. First of all, you should be able, when you are explaining a circuit, first identify everything that is labeled the same. You can see here in the circuit, the only thing that has the same label is CR1. So this contact CR1, the job is to copy everything that happens here, but unfortunately it is a normally closed open, so it's going to be doing the opposite. When the output CR1 is active, this one is off. When the output CR1 is off, this one is on. So that's what it's going to be doing. It's a normally closed contact, so it's going to be doing that. All right, let's go to 2. So 2, what did I say? They say design a PLC circuit that will operate as follows. When you press X, so let's create another page and do this one. So when you press X, let's come here. When you press X, so X is that X? So let's read. So when you press X, so no, they don't say when you press, we say when input X is activated, so that's an input contact, CR1 will be energized. So CR1 is the output of X. So when input X is activated, CR1 is also activated. So that's what it says. CR1, sorry, we're somewhere here. So when input X is activated, CR1 will be energized. When the input X is released, that's what they say, when input X is released, the control relay coil CR1 will be latched by the contact CR1. So there is a latching contact. There is a latching contact there. So it says when you release these contacts here, what happens? There is a latching contact that should be labeled CR1 here to hold power for the output. That's what happens there. So now when input Y and input Z are closed simultaneously, this is an AND gate, Y and Z are closed simultaneously, CR2 will be energized, which will open the CR2 contact and de-energize. So let's see. CR2 will be energized, which will open the CR2 contacts and de-energize CR1. So this is what they say. They say that somewhere here you have two contacts which are in series. That's an AND gate. Simultaneously you have Y here and you have Z there. They are controlling CR2. So that's what's happening there. But at the same time, there is a contact here that's also controlling CR1, which is a normally closed contact, and that contact is also labeled CR2. That's what it says. So if this output is activated, it also does some action on this normally closed contact, which will open eventually because it's a normally closed contact. This contact here that is labeled as the same as the output is copying everything that happens here. Since this one has received some power, this one also need to receive some power. But the problem here is this one is a normally closed contact. So when it receives some action, instead of closing because it was already closed, it's gonna open. So that is exactly what's happening there. So when it opens, what happens? When it opens, it automatically de-energize CR1. So let's read on and see if there is any other thing, and so which will open and de-energize CR1. So that's actually the circuit. So don't forget to always, that's actually the circuit. So don't forget to always end your circuits with a AND symbol. So you have an AND symbol there, that's your AND symbol, and you're good. So you can always include the other parts, or you can just leave it like that. It's also fine, but yeah, this is correct. So let's go, let's read on. 5.2, give the schematic symbol for each of the following components in the ladder diagram. So they're talking about output device. So an output symbol is going to be like this. That's the symbol used for output in the ladder diagram. Normally open contact is going to be like this. That's a normally open contact, and you have 2 marks for that. So this was the easiest part. All right.